Alrighty, well today we're taking a look at recitation 7 for materials. And I'm just going to do the second part where we start getting into the binary eutectic diagram because it's a little bit more complicated. Right, so we have a 40% tin, 60% lead alloy at 150 degrees. Right, at what phases are present, right? So first, our 40% tin here. We have our 150 degrees Celsius over here. So we're just going to find where these two intersect. They intersect right here, which is within our alpha and beta region, which means that those are going to be our two phases present, alpha and beta. Beta. The compositions of these phases. So for this one, we're just going to look at this temperature line, right? And we can just extend that all the way across, keeping it horizontal. And where it intersects on this side is our alpha region in here. All right, where it's going to intersect with the alpha region, we drop that line down to the axis. It's about 10, we can estimate. But that's going to be our composition of our alpha phase. All right, so our alpha phase, because again, we're looking at the weight percent tin, 10, 20, that's it, 10, halfway between 0 and 20, right? So alpha is going to be 10% tin, and then the complementary percent, 90% lead. PB, right? And now we do the same thing for beta, where we follow the line all the way over to the other side, all the way over this way, to this side where it intersects with our beta region. Get that? We drop that line down to the axis. And we can eyeball that and say it's about 98-ish, right? 98%. So that means, and again, that's our, not CL, C beta, 98%. And since we're still just looking at this same axis, right? We're just looking at the weight percent tin for this. So that's going to give us that it's 98% tin. And then our complementary percent, 2% lead. Right? Calculate the relative amounts of each phase is present in terms of the mass fraction, right? So this is the lever rule that we were looking at, right? These are going to be our W alpha and our W beta, right? So if I look up here, right, if I erase, I'm not going to erase these lines, right? So we have it coming across. It's great. So when we're doing our lever rule, right? If we're over on this side, right? If we're coming this way and we get just across this line, right? We're very close to just being pure alpha, but we have just a little bit of beta, right? So that means that we're like right here. This little bit is going to be our beta, and this bigger bit is going to be our alpha. And that's like our percentages, right? So that's the part of, that's why it's like the opposite side, right? But we're looking at our point again here, right? So for our weight percent alpha, we're going to take our section between here and here, because again, we're going opposite from where it intersects. So we're going to do this side, which is going to be our composition of beta minus our composition of the actual thing. So that's our C beta minus our C of the thing, divided by our total, which this entire length of this line is going to be our beta minus our alpha. Right? So C beta minus C alpha. Right? And you can solve that out with all the numbers and everything. Now for beta, we do the same kind of procedure. I mean, you could do 1 minus weight alpha, because again, they have to equal 1. If you add them together, they have to equal 1. So you could do 1 minus alpha to get the beta. I'm just going to solve it out. I'm going to get the formula for it anyways, right? So our beta is this side, right? Because again, we intersect over here, so we're going to the opposite side. So this is going to be this smaller piece is going to be our C naught or C0, whatever, minus our alpha, C alpha, to get this chunk. And then again, it's this over the full length again. So our C naught minus C alpha to get that left side divided by, and again, the whole thing is just the larger one, C beta, minus the smaller one, C alpha, right? So these are going to be our two formulas, and you can plug in for each of those because we already have our C alpha, C beta, and our C naught was given by the problem, 40%, right? And you're going to use the numbers like the 98 and the 40 and the 10 for these, and it's going to give a decimal answer, which you can then multiply by 100 if you wanted it in terms of a percent. Now the volume fraction, this equation was in one of the lecture slides, but we didn't actually get to it in lecture. That's V alpha is weight percent alpha divided by composition alpha over weight alpha over composition alpha plus weight beta over composition beta, right? Oh, sorry, that's it's not composition, it's density alpha, density alpha, density beta. I'm sorry, not composition. I'm just thinking about the compositions from the tie line rules, right? So to get our density of alpha, we're going to use that's when we use the composition of alpha, right? So we know it's 10% tin, 90% lead. So for alpha, our density is going to be, if we do tin, right, 7.24, 7.24 times our 10%, 0.1, plus our lead, which is 11.23, times our 90%, that's going to give us the density of alpha. So again, because that's the composition of alpha, just weighted, right? And then same thing for beta. So beta was 98% tin, 2% lead. So we get our tin 7.24 times the 0.98% plus our 11.23 times our 0.02. And that's going to give us our rho beta. From there, we can plug into here because this is just going to be like generally the mass of the thing divided by the total mass or whatever it is. Volume, all that mess. I don't know. I don't know how it was derived, but I know this is what was given by the thing. And the beta is this. This is going to be the same equation just with beta over beta on the top. And again, divided by this total. I'm just being lazy. I don't want to write it twice. But yeah, so you can plug these values into here. And again, we have our weight percent up here, so we can calculate this. And for this one too, you can use these multiplied by 100, like, so if it was like 0.5 something, I think one of them is maybe, oh no, 0.6 something, right? 0.65, somewhere between 0.65 and 0.67, then we'd use like 67%. Or you could use either, because I think you could use either because it's like a ratio, but just keep it consistent and check your work. I used not the decimals. Did I use the decimals? I don't remember. One will give an answer that looks correct. The other one will give an answer that's not correct. My bad. So our next question, we're looking at another binary eutectic phase diagram and the microconstituents. Right? So I didn't have workspace for question 2, so I'm just going to put them both in here. But you have a 30 weight percent tin thing, and it's heated to a temperature within the alpha and liquid region. The mass of each fraction is 0.5. So for this one, we're just eyeballing it to see where it looks to be about halfway between. So we're looking for 30 and 70. So 30% here. We're kind of eyeballing it to see where it looks to be about halfway between each side. So that and that. I don't know, I drew it a little crooked. About there. I don't know, that looks to be about half and half to me ish. So that's about 225, right? So that's 225 degrees Celsius. Again, it's just kind of eyeballing it right here. And the composition at each, this is where you're going to actually draw the horizontal line at the temperature and find where it intersects with each line, right? So we have alpha and liquid in this. So we drop down this all the way down to the axis to get about 15%. So our alpha composition, again, because we're intersecting with this alpha region here. All right, so our C alpha is going to be about 15%. And again, since we're looking at the primary thing, we're just getting the percent tin. And that's going to be, what, 85% lead, right? And then we do the same thing for our liquid composition. We just find our intersection and drop the line down to the axis. That's about 45%. That's our C liquid. It's going to be 45%. And again, this is just our percent tin. And then we're just going to get the complementary percent for lead. All right. So that's those two, the compositions of the two phases. And now we have the microstructure of our lead tin alloy at about 180 degrees, which is just below our eutectic temperature, right about there. It has primary beta and eutectic structures, which means it's going to be on this side, right? Because over here it would have primary alpha forming, but over here is where we get our primary beta. So that means our concentration is going to be somewhere on this side, right? So if the mass fractions of the microconstituents is 0.57 and 0.43, right? So 0.57 primary beta, 0.43 eutectic, determine the composition, right? So for this one, right, so we want our weight composition of beta prime or beta primary to be 0.57 and our eutectic to be 0.43, right? I'm just going to focus on our primary beta for right now because I think that's easier, or at least it was for just my brain, the way my brain thinks. Right, so somewhere in here, just drop a line wherever, right? That's going to have that composition of our primary beta and our liquid. Well, because our liquid is what's going to just go through that eutectic reaction. So whatever our liquid is, that's what's going to become this weight percent here, right? So really, since we're close, we can just kind of look in this region more so. So so our primary beta, what has formed wherever we are here, it's going to be from some CO. It's going to have our composition beta over here, the 97.8, and this is going to be our composition liquid in here, the 61.9. Composition liquid is going to be our composition of the eutectic thing, and our beta up here is going to be our composition of our primary beta, right? So if we have our weight percent, our mass fraction of beta, of primary beta, we can solve for that in terms of this here, right? So if we're looking for our primary beta, we're going to take the opposite side, right? The opposite side to where it intersects with beta. So that's going to be CO minus CL. So it's going to equal CO minus CL over this whole zone, which is going to be C beta or C beta prime, I guess, or either way, C beta minus CL. Right, so if you say that's C beta minus CL. All right, and again, these numbers I'm taking from here. So it's 97.8 and 61.9. I'm just going to plug those in. 97.8, 61.9. Beta is CO minus 61.9 over 97.8 minus 61.9. Now from here we can use this, and again we're setting that equal to our original weight percent beta, weight percent primary beta, and we can get our 0.57, and we can use this equation to then solve for our C naught, or our original composition of whatever the alloy is, right? And I don't remember what the exact number is, and then but afterwards you can check it, because whatever isn't this is obviously over in this one. So if we solve for some concentration, we can check it by doing the same thing that we did, finding the mass fraction in terms of the CO and set it equal over here. We can check it by doing the same thing with our eutectic mass fraction. So that's equals 0.43. This one, since we're looking at the liquid side, it intersects over here, so we're going to go opposite side. So that's going to be C beta minus CO. C beta minus CO all over. And again, this is the whole length of the line. C beta minus CL. C beta minus CL. And plugging in our numbers again with our 97.8 minus CO over beta was 97.8 minus CL was 61.9. And again, because again, that's set equal to our original 0.43. That you could also solve for CO in this, right? Because we have one equation, one unknown, one equation, one unknown, and you should get the same answer from both of them. All right, well, thank you very much for watching this video. I hope you found it at least a little bit helpful. I try to do my best to explain a little bit of materials, but I have a bit of trouble in this class sometimes too. So if it didn't make any sense, let me know if you have any more questions about this recitation or anything else that you might want me to go over, and I will do my best to try to explain them, because I guess Sydney explains stuff.